Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Afiqah binti Abdul Wahab. So today we would like to present our mini project. The title is Digital Dice Roller. So for team members consists of Aisyah Humairah, Nur Afiqah and Siti Sarah. Okay, for the project description, digital dice roller is an electronic device that works like a normal six-sided dice. It uses 7-segment display and a random number generator. Instructions for the user are shown on LCD screen. When user press 0 on the keypad, the system will generate random number from 1 until 6 and display result on the 7-segment display. To improve user experience, the buzzer will produce sound during the rolling process. Okay, for the block diagram consists of 3, which is input, controller and output. For the input, we have keypad 0 and connected to the port A. Next one is controller. We use Dragon board, and for the output is buzzer, LCD and 7-segment display. Okay, so for the flowchart, the system starts when display hello push keypad 0 on LCD screen. Then idle state red LED is on, which is using RGB LED. When keypad 0 is pressed, green LED is on and buzzer will display the sound and also generate random number from 1 until 6. It will display a message on LCD, display number on 7 segment and wait for the 3 seconds and it will clear the display. And the program is looped from idle state, which is red LED is on. Okay, for the coding with command, the figures show that the constants and variables used in digital dice roller system. It includes delay values for LCD timing, LCD control bits, and a pin connection for the RGB LED and buzzer. It also defines musical notes delay and variables used to store temporary data and a random number, including LCD connection to port K of the HCS12 microcontroller.
Next, we go to the system initialization, which is the main program. Program starts by setting the step pointer to ensure proper subroutine and interrupt handling. Timer module is enabled for delay and timing operation. Keypad pull-up registers are activated to ensure stable key detection. 7-segment display and RGB LED pins are as output. Red LED is turned on by default to indicate system is in idle state. Buzzer is set as output and kept off during the startup. LCD is initialized to prepare it for displaying message. All variables are clear to avoid undefined values. An initialized message is displayed on the LCD to greet the user. This part of the code initializes all hardware components such as timer, keypad, display, LEDs, buzzer, and LCD. It ensures the system starts in a safe and known state before executing the main program. This slide shows main loop operation in this coding program. Idle mode, red LED on, waiting for keypad input. K pressed, green LED on, buzzer activate. Generate random number 1 to 6 using timer. Display result and return to idle. This loop controls the system behavior. It waits for a keypad input, activates visual and sound indicator when a key is pressed, generates a random number between 1 and 6, display the results, and then returns to idle mode. Next, output and reset process. Display random number on 7 segments. Hold output for 3 seconds. This clear display and reset system show instruction message on LCD. After generating the random number, the system display in on the 7 segment display for 3 seconds. The display is then cleared. The LCD shows the initial instruction message again, and the system returns to idle mode waiting for the next key press. Next, we will go to output and feedback. Display result message on LCD. Hold output for 3 seconds. Play do re mi buzzer for 5 seconds. This part of the code handles user feedback. The LCD display a message to inform the user. A 3-second delay allows the result to be seen clearly, and a do re mi buzzer sound is played for 5 seconds to indicate successfully operation. This slide shows about subroutines. Generate buzzer tones using on-off timing. Control sound frequency and durations. Provide delays for buzzer and LEDs. Improve sound clarity and system timing. These subroutines support the main program by generating buzzer tones and handling timing delays. They control how long the buzzer and LEDs stay on or off, ensuring accurate sound output and clear visual indication. Next, we will go to LCD initialization and timing. Firstly, generate 1 millisecond delay using loop. Add startup delay before LCD commands. Configure port K as LCD output. Initialize LCD in 4-bit mode. This part of code handles timing and LCD initialization. A 1 millisecond delay is treated for accurate timing, and proper delays are applied before sending commands to the LCD. The LCD is configured in 4-bit mode to reduce pin usage while maintaining reliable display operation.
This part of the code is used to control the LCD display. The program uses the RS pin to choose between command mode and data mode. When the code runs cell_ins, it sets the LCD to command mode, so the LCD can receive instruction like moving the cursor. When the code runs cell_data, it sets the LCD to data mode, so the LCD can show letters and numbers. After that, the program moves the cursor to line 1 by sending the command 18, and then it prints the message on the first line. For line 2, the program sends the command C0 to move the cursor to the second line, and then it prints the message there. This code helps the LCD show text in the correct position on the screen in a simple and clear way. This part of the code is used to send data and character to the LCD screen. The message_out routine sends a message to the LCD 1 character at a time. It loads a character, sends it to the LCD using WRT_byte, then moves to the next character until the whole message is shown. The WRT routine is used to send 1 full byte to the LCD. Because the LCD works in 4-byte mode, the byte is split into 2 parts. First, the upper bits are sent, then the lower 4 bits are sent. Each time the data is sent, the program gives a small pulse to the enable pin so the LCD can read it. Then, WRT_enable routine helps send only 4 bits at a time to the LCD. A short delay is also added so the LCD has enough time to process the data. This code makes sure that every character is sent correctly and appears properly on the LCD screen. Lastly, this part of the code is used to give a signal to the LCD, also create small delays. The enable_pulse routine sends a short pulse to the LCD enable pin. This pulse tells the LCD to read the data that was just sent. First, the code turns the enable pin on, then it turns it off again. This on-off pulse makes sure the LCD accepts the data correctly. After that, the delay routines like delay_10ms, delay_5ms, and delay_50 micros. or are used to wait for a short time. These delays are important because the LCD needs a little time to process each command or character. The del1 loop simply counts numbers to create the delay time. At the end, there is a message data section that stores the text such as "Hello, please push keypad 0 and here's your number." This message will be sent to the LCD and shown on the screen. This part of the code helps the LCD read data properly and display the correct message without error. Innovation. The digital dice roller is an electronic device that works like a normal 6-sided dice. It uses a 7-segment display and a random number generator. Instructions for the user are shown on an LCD screen. When the user presses the 0 key on the keypad, the system generates a random number from 1 to 6 and displays the result on the 7-segment display. To improve user experience, a buzzer produces sound during the rolling process. In the conclusion, this project successfully developed a digital dice roller using the HCS12 Dragon board, a keypad, a 7-segment display, a buzzer, and LCD screen. The system generates a random from 1 to 6 when the 0 key is pressed, simulating a 6-sided dice. The result is displayed on the 7-segment display, while the LCD shows instruction and system message to guide the user. The buzzer provides sound feedback during the ruling process to improve user interaction. This project demonstrates effective use of peripheral interfacing, random number generation, and real-time system operation. The system can be further improved in the future by adding features such as LED animation or wireless control.